So to begin our analysis, let's first consider the brightness that we can expect on the first photo plate. So for then this B1 of x, what we are expecting here, and I'll give us a sketch of it like so, right? This is a function of x. In this case, it's actually a fairly simple determination. There's a certain brightness that arrives on the surface of my blocking filter from my source, right? And that brightness, of course, technically speaking, you might expect it to be a little brighter, say, for the lower portions of the blocking filter, because those technically are a little bit closer to my source as compared to the further up ones. But the truth is that I've chosen this radius r to be so large, much greater than the portions through which the particles actually can pass, that the brightness actually, in the regions where electrons or photons can actually get through, that brightness from my source is essentially constant, because this r is much greater than the slight distances. There's only a slight fractional change in the distance from my source. So I can call that constant incoming brightness that falls on my filter, I can just give that a name. I will call that B0. That's the brightness that arrives on the left side of the filter. What actually makes it through onto the x-axis, because these are here directly right next to each other, is simply this incoming brightness times the fraction of the brightness that I'm allowing through via my filter. And that function is this transmission function. So this will just be the originating brightness times my transmission function of x. And if I want to write it out mathematically, I will then have B0 times e to the minus x squared divided by twice sigma squared. Now, that's the brightness. From that, I'm supposed to be able to determine the probability as a function of x. And the brightness really is giving me a histogram. So here I might sketch it here as brightness, but I'm going to turn this into probability. The brightness just gives me the histogram of where the particles are landing. And that histogram is basically the probability distribution. The only difference is that the probability distribution, to obtain that, we have to divide by the total number of arriving particles to turn it into a valid probability. So the probability distribution is proportional to the brightness. And the big question then is, what will that proportionality constant be? Now, to determine the value of that normalization constant, we use the normalization condition. And the normalization condition, as we had discussed previously, simply states that if I integrate from minus infinity to infinity my probability distribution, I must always get the exact value of 1. Now, I can insert here my probability distribution, which then, integrate with respect to x. So I'm now going to insert this probability distribution into here and integrate. When I do that insertion, you will notice I have these two constant factors, which I could immediately pull out, alpha B0, and then I'm left with the integral from minus infinity to infinity of a standard Gaussian function, e to the minus x squared over 2 sigma squared integral dx. And this actually is a known standard integral. The value of this integral is, well, if it were just a regular Gaussian without anything here, just a pure x squared, I know the result would be square root of pi. What happens when we have constants below the x squared, and I just happen to have this memorized, it's a good thing for you guys to memorize for Gaussian integrals, is that what multiplies the pi is whatever appears here in my denominator. So what multiplies the pi in this case is a 2 and a sigma squared. So from this, I can immediately then determine the value of alpha times B0. It must equal 1 divided by, right here's alpha B0, this product had to be 1, so it's 1 divided by the square root of 2 pi sigma squared, and so then that tells me my absolute result for my probability distribution. I could sketch it for you here. P of x then is going to equal alpha B0 times my Gaussian, and alpha B0 has this value, so it's 1 over the square root of 2 pi sigma squared. Sigma squared is inside my square root, times an e to the minus x squared divided by 2 sigma squared. And that then is my probability distribution in position, which will actually have a standard deviation of sigma, which is another way of saying the Heisenberg uncertainty in x, delta x. Terrific. So that has then determined for me everything I need to know about the probability distribution of these particles along the x-axis.